today's topic is chemical properties of phenol. So phenol is benzene ring, the aromatic ring with OH. This is what phenol is. So phenols show many reactions similar to alcohols because of the OH group. So the OH group is there with the benzene ring, aromatic ring. That is why it behaves as a alcohol in some reactions. But still it behaves differently from alcohol because that is due to the direct attachment of OH with benzene ring. So over here what we have seen in alkyl alcohol, over here also the cleavage will take place. Over here cleavage, it's not a cleavage but the replacement of OH, H from the OH or the H from the benzene ring. So only two types of reactions can happen. So one is the hydrogen from the hydroxyl group replaced by something else, and or an atom or a molecule will replace a hydrogen from the aromatic ring. Okay, so that is what I have classified like those reactions involving OH group and reactions involving in the benzene ring. So reaction involving OH groups actually acidic character, and with sodium and sodium hydroxide, reaction with sodium and sodium hydroxide, and the reaction with zinc, reaction with acylation, that means acetic anhydride, and with the PCl5, phosphorus pentachloride. So these are the reactions involving in OH group, that means which replaces the hydrogen atom. And over here the reactions involving in the benzene ring, which is over here the hydrogen from the benzene ring will replace in these reactions. The reactions are electrophilic substitution reaction, in that bromination, nitration and sulfonation. And the other two reactions are naming reactions, very important reactions, Coles reactions and Riemer-Tiemann reactions. So in today's class we are going to see both the reactions with OH and reactions involving in benzene ring. Come on, let's see. Reactions involving OH group. Under that, the first subtopic is acidic character. So how will you say it is acidic? Phenol is acidic. Actually phenol behaves as a weak acid. So that means partial dissociation, right? And it turns the blue litmus paper to red, or blue litmus solution to red. So basically acid turns blue litmus to red, but the alcohols are neutral to litmus. Alcohols, in the sense I'm talking about alkyl alcohol, right? So phenols react with alkali metal like potassium, sodium, lithium. So it reacts with alkali metals and their hydroxides like lithium hydroxide, sodium hydroxide, potassium hydroxide to form the salts of these phenols. So that is phenoxides or phenates. So over here I have given two reactions with sodium. So same type of reaction only will happen with lithium and potassium too. So over here 2 moles of phenol reacts with Na, 2 moles of Na, which is sodium, and over here the replacement of hydrogen is taking place, and like acid. So what will happen in acid? If you put sodium, you will get a salt and the hydrogen evolves. Same thing happens over here too. And with the hydroxide, sodium hydroxide also, this behaves as over here, if you consider this as a weak acid and this is the alkali. When acid and alkali reacts together, it's a neutralization reaction which gives salt plus water. Over here also same thing happens. You are getting phenoxide and the water you are getting. So same like neutralization reaction. So this proves it is acid. And phenols are unable to decompose carbonates and bicarbonates. For example, sodium carbonate Na2CO3, sodium bicarbonate NaHCO3. So these the phenols cannot decompose these carbonates. The reason is it is weaker than carboxylic acids. Okay, and phenols are more acidic than alcohol. So phenols are acidic than alcohol, that is why you are getting the blue litmus turns red. So this is more acidic than phenol. Okay, but it's a weaker acid than carboxylic acid. So now we will see reaction with zinc dust. Okay, so over here phenol, when it reacts with zinc dust, so you need to heat this mixture. By heating this, you will get benzene. That means zinc will oxidize. Okay, so zinc will oxidize and the benzene ring will get back the hydrogen, so you will get the benzene ring as a product. And the next one is reaction with acetyl chloride and acetic anhydride. We commonly say it as acylation reaction. So when phenol reacts with acetyl chloride, so CH3COOH is acetic acid. Over here the OH is replaced by Cl, so it is acetyl chloride. When it reacts with phenol in the presence of pyridine, pyridine is the benzene ring which has nitrogen, which we have already discussed about it. So in the presence of pyridine, the reaction takes place and you will get phenyl acetate. So acetate, like esterification, the HCl evolves, the minor product evolves and you will get phenyl acetate. So phenyl acetate, right? And phenol with over here acetyl anhydride, acetic anhydride, that means CH3OH, CH3COH, CH3COH. In that water, if water evolves, you will get this acetic anhydride. So when this reacts with phenol, the H reacts with one of the acidic group and forms the acetic acid, and the other one reacts with the benzene ring and forms phenyl acetate. So two different products you will get, that's it. But over here, if the same reaction takes place with in benzylation, it will react with benzoyl chloride. So when it reacts with benzoyl chloride, you will get this reaction is called Schotten-Baumann reaction. So this is very important reaction. Benzylation. In benzylation, you will get phenyl benzoate. So you will get over here benzene ring will be there. So that means phenyl benzoate. So benzylation of phenol in the presence of alkali. Over here we are using sulfuric acid with concentrated sulfuric acid with acetic anhydride, and pyridine. In the presence of pyridine, the acetyl chloride reacts with phenol, but over here alkali. Okay, this is called Schotten-Baumann reaction. And then reaction with phosphorus pentachloride. So this type of reaction we have seen many with alcohols. So the same way, replacement of OH in phenol is difficult by the halogen. So the halogen acid does not react. Halogen acid in the sense what? HCl, HBr, HI, HF. These are all halogen acids, right? So these does not react and you will not get a chlorobenzene. So to get the chlorobenzene, what we have to do? We have tried PCl3 with alcohol, but over here the PCl3 will produce phosphorus esters. So you won't get chlorobenzene. So that we are using PCl5, but over here the partial replacement is taking place and you are getting a minor product as chlorobenzene. But this yield is very poor, so that the main product will be triphenyl phosphate. You will get this phosphate as a major product, but the chlorobenzene will be a minor product. Now we are in reactions involving benzene ring. So over here, first we are going to see halogenation. Halogenation is nothing but substitution reaction. So over here, the monohalogen derivatives. So monohalogen derivatives, like over here in these two products, you are getting only one halogen. That is what monohalogen derivative. This can be prepared by halogenation reaction. Over here at low temperature, at 243 Kelvin, at low temperature, in the presence of CS2 or CCl4. So carbon tetrachloride or carbon disulfide. In the presence of this, the bromine reacts with phenol and you are getting two different products. Okay, so orthobromophenol and parabromophenol, right? Or you can write 2-bromophenol or 4-bromophenol. So over here, on using water as a solvent, If you use water as a solvent, the phenol with bromine water leads to 2,4,6 tribromophenol. Okay, that means excess of bromine. If it is excess, what will happen? That is what we have shown, like 3 moles of Br2. So over here 3 of the hydrogen is replaced by Br. So 3 hydrogen in the sense that this opens the position 2,4,6. That means 2 bromo, 2,4,6 tribromophenol. So tribromophenol, which gives you white precipitate in this reaction. This is what halogenation is. And the same way, even in nitration too, nitration of phenol with dilute nitric acid leads to mononitrophenol. Same way, but over here 293 Kelvin, right? So in if you take with a concentrated HNO3, so concentrated nitric acid and also in the presence of concentrated H2SO4. So do you remember this mixture? So we have seen this two mixture, 1:3. This mixture is called nitrating mixture, right? So by mixing these two, you will get NO2. So more number of NO2. That means over here 3 moles of concentrated HNO3 and in the presence of H2SO4 they have given. But still it is called nitrating mixture. So over here you will get NO2 from this mixture. Those NO2 reacts with same. It opens the same position 2,4,6. So over here 2,4,6 trinitrophenol, and it's commonly called picric acid, right? It is commonly called picric acid. But the yield of picric acid is very low in the previous reaction because the phenol oxidized by nitric acid. We know nitric acid is a very good oxidizing agent, right? So we have to do indirect method to get the picric acid. So over here the indirect method is, first we will add concentrated H2SO4 with phenol. At 373 Kelvin, the sulfuric acid will react with phenol and you will get two different products, orthophenol sulfonic acid and paraphenol, which means 1,4. So paraphenol sulfonic acid. So you will get two different products. So in this mixture you will add concentrated HNO3 and then you will heat it. So by heating these mixture you will get a picric acid because HNO3 gives NO2. So and the NO2 binds with phenol, which leads to picric acid, which means 2,4,6 trinitrophenol. Now the next reaction is sulfonation. Sorry children, it's a lengthy video I know, but totally if you see all the chemical properties together, it will be easier for you to understand. That's why. So now sulfonation. In sulfonation over here, the paraphenol sulfonic acid, right? So phenol when it reacts with sulfuric acid, as we have seen in the previous thing, the phenol when it reacts with sulfuric acid at 373 Kelvin with concentrated H2SO4 leads to paraphenol sulfonic acid, which means 1,4. So phenol sulfonic acid, paraphenol sulfonic acid. If the temperature is less, like 293 Kelvin, so at 293 Kelvin with same concentrated H2SO4, this leads to orthophenol, 1,2 position, orthophenol sulfonic acid, HSO3. So over here the hydrogen from the replaced hydrogen and the hydrogen from the acid goes as H2 gas, hydrogen gas. And next one, Cole-Schmidt reaction, which is a very important reaction. The naming reactions all are very important. And over here sodium phenoxide. Actually we'll get sodium phenoxide from phenol with Na or with NaOH. You will get this sodium phenoxide. So phenol to sodium phenoxide, and sodium phenoxide plus CO2, carbon dioxide, at 400 Kelvin, that to 6 to 7 atmospheric pressure leads to this product. This is the intermediate product. By rearranging it, you will get sodium salicylate. So benzene with phenol OH and COONA, that shows sodium salicylate, because OH with COOH is salicylic acid, right? So sodium salicylate. So over here on acidification, this reaction is called acidification. Over here we are using dilute acid. So on acidification, you will get the product salicylic acid, which is orthohydroxybenzoic acid. Orthohydroxybenzoic acid or 2-hydroxybenzoic acid. That's a position of the acid. 2-hydroxybenzoic acid. Sorry, position of the alcohol, because acid you will consider as 1 over here. So in that way, 2-hydroxy. Hydroxy position is 2. So 2-hydroxybenzoic acid. So if this happens over here, we are using 400 Kelvin. If this reaction happens at 573 Kelvin, you will get para-hydroxybenzoic acid, okay, which is 4-hydroxybenzoic acid. And then Riemer-Tiemann reaction, again another important reaction. So in this, phenol reacts with chloroform. This reaction I think already we have seen when we were doing chloroform, properties of chloroform. So when this reacts in the presence of NaOH, over here the HCl and water releases, because the HCl from the chloroform releases, so that over here CHCl2 and Na will bind over here and removes the H, so that HCl and H2O releases, and you are getting the intermediate. That intermediate leads to, when on hydrolysis with sodium hydroxide, again 2 HCl releases. That means these 2 Cl releases, and you are getting again the intermediate substance. On over here, when dehydration taking place, you are getting an aldehyde. So this aldehyde group again on when it reacts with dilute HCl, over here the NaCl removes Na, the Na binds with Cl over here, and the H binds with the benzene ring, with phenoxide, and this leads to orthohydroxybenzaldehyde, which is otherwise called salicylaldehyde. Okay, this is a major product, and if you get minor product, the minor product will be para-hydroxybenzaldehyde. Okay, that means 1,4 position. So para-hydroxybenzaldehyde. And the yield of picric acid in that reaction is low, because the phenol oxidized by nitric acid. Already we have seen this concept, because nitric acid is a very good oxidizing agent. So over here we are using indirect method to prepare picric acid. In this method 90% picric acid you will get. So what is that method? Phenol, when it reacts with concentrated H2SO4 at 373 Kelvin, you will get orthophenol sulfonic acid. So orthophenol sulfonic acid. 1 minute, children. Do you remember, children, we have seen this? Okay, sorry children, I think we have done picric acid, right? So we'll move on to Riemer-Tiemann reaction. So again, we have seen this, right? So we will get para-hydroxybenzaldehyde and orthohydroxybenzaldehyde. Yeah, by mistake I have moved on to picric acid again, but actually the Riemer-Tiemann reaction, there is one more Riemer-Tiemann reaction, because why I am saying one more, over here we are getting salicylaldehyde as a product, right? And the other Riemer-Tiemann reaction leads to salicylic acid. Over there salicylaldehyde, over here it is salicylic acid. Okay, so the phenol reacts with carbon tetrachloride. This leads to the intermediate, and which the intermediate, when on hydrolysis, like the previous one, on hydrolysis you will get this intermediate. That means all the three chlorine replaced by OH group from the NaOH. Okay, and over here on dehydration you will get this as an intermediate. This intermediate again on hydrolysis you will get ONaCOONA with benzene ring. This is also also an intermediate which leads to acid. Which leads to the product which is called salicylic acid. 2-hydroxy benzoic acid. Again, as I said, 2-hydroxy, because this will you will take it as 1 because it's a salicylic acid. So 2-phenol. So over here, rather saying phenol, you will write 2-hydroxy. The position of hydroxyl is 2. 2-hydroxy-benzoic acid. And the minor product is 4-hydroxy-benzoic acid, which we are using in preservative, in cosmetics and ophthalmic solution. The eye drops and all. As a preservative, we are using this 4-hydroxy-benzoic acid, right? So, but the major product will be salicylic acid. Yeah, that's all, children. The chemical properties of phenol.